Hello. I did something I hopefully don't do often, which is I forgot to hit record at the start of lecture today. So the first half of today's lecture is a re-record from what I had said in class today. Generally, I go a little bit faster, so if you're watching this at home, hopefully it'll be a little bit quicker than we talked about some of this stuff in class, if that's a plus side at least. And then the second half was, I started recording about halfway through. Okay, so this question here, this is an extra problem I added to the lecture module. This is like chapter 1 extra problem if you want to look for it and to be able to write onto it. But describe each compound below as an atom, molecule, compound, and or mixture. So which terms apply? Let's look at box 1. So for box 1, the fact that you see two different atoms connected together makes this a molecule. So this is definitely a molecule. The molecule is comprised of atoms, but when I say atom, I would think that the things in box 4 are being described as being atoms. So here I see different atoms. So I see atom, A, maybe that's helium, for example. Maybe this atom here is xenon, for example. I'm just using examples of the noble gases because they're the only gases that exist as actual atoms in their natural form. And so we have atomic gas mixture for box 4. So these are representing an atomic, or let's call this a mixture of atomic gases. So I just want to be not entirely confusing when I look at the molecules in box 1 and say that those are a molecule, not an atom. Though the molecule is comprised of atoms, of course, but we're not calling the molecule an atom. So a molecule is a collection of at least two atoms bonded together. And then a compound would require that the molecule contain two different elements. And so I'd have to have a different shading for the atom to imply a different element. So I have the same element connected to itself. So this is just a molecule, not a compound. Definitely not a mixture because there's only one molecule present. Box 2, I see that molecule and then a different molecule. And then the second molecule is a compound, but it's still a molecule. It's a molecule too. We often call this thing that I've circled here, we call it a molecular compound. And then the other one we don't call a compound, this is just a molecule, not a compound. And so we have molecules, we have compounds, but this is also best described as being a mixture. So it's a mixture of a molecule and a molecular compound. And then box 3 is just a compound. It's also a molecule, so it's a molecular compound. Apologies for the terrible handwriting, but molecular compound. So getting back into where we were in class on Wednesday, we were talking about sig figs. And so the digits in a measured quantity, including the uncertain one, are called the sig figs. And so if I write 125 grams, that this implies that there's some inherent uncertainty in the last digit, though we still have a value, we say, that has 3 significant figures. Now, the issue of sig figs is if I were to write 125.00, that's 125 grams with greater precision. So having more digits increases the precision and the values. So this is 125 with 5 significant figures. So the difference between 125 grams and 125.00 grams is the preciseness of the value. When we're rounding calculated numbers, we have to pay attention to the significant figures so we don't overstate the accuracy of our results or sometimes understate the accuracy of our results. So when we start doing addition, subtraction, when we do multiplication and division, we have to come up with our sig fig rules for those 2 steps. Those are going to come up in a couple of slides. Before we get there, let's just try to make sure we understand what significant figures are trying to portray. And so I did this example of, imagine you have an object, doesn't matter what it is, you have some sort of an object that has some sort of actual length. The object, we could use the best known device and probably measure the length of this object to probably like 6 or 7 placeholders if we had a really, really precise scale that we were using. Now imagine we're not using a precise scale. Let me try to do something a little different here than I did before. Let's try to use scale 1, scale 2, and let's use scale 3. Imagine you have 3 different types of rulers you can use. And imagine that ruler 1 is this here, that it's on the increment of about 5 to 10 centimeters. And so when I'm looking at this object here, you can see that it's definitely not 5, definitely not 10, somewhere in between. I can interpolate between my scale markings. I can probably interpolate this to probably about 9. So let's say scale 1, I'm interpreting that this measurement is 9 centimeters and that the number of sig figs that I get here is approximately just 1. So it's like 9 plus or minus 1 centimeter. Okay, there's obviously going to be better rulers that we can use than this one here. So let's imagine we use a different ruler that has markings that go every centimeter. So if I have markings every centimeter, and if I roughly sketch them correctly, 6, 7, 8, 9, 10. So this would be 6 centimeters, 7, 8, 9, and then 10. What we can see is that this object here is actually probably halfway between. So I can interpolate now, maybe even it's slightly over halfway between the 8 and the 9 marking. Like I might say that this marking is at about 8.6 centimeters. Now maybe you look at it and think it's 8.5, maybe somebody else looks at it and thinks it's 8.7. The fact that we're arguing that it's somewhere between 5, 6, and 7 kind of show that this has some uncertainty to it, but also that it is still significant because we know it's not 8.0 or 8.1, it's not really 8.9. So we can really make out that measurement now to 2 significant figures, and we're just arguing over what exactly that value should end in. And so then let's lastly imagine we have improved our scale again, and so then let's imagine we get even more scale markings. So if you imagine the scale markings now are every 10th of a, I guess I didn't do what I mentioned doing, which is taking a scale marking here on a third scale, and we go with 8.1, 2, 3, 4, 5, 1, 2, 3, 4, 5. We have a better scale, and now we can try to interpolate that measurement. So what we're going to want to do is line that up here and then line it up between the 8.5, the 8.6 marking, let's say, and zoom in real close or try to look as carefully as we can. And this looks like maybe 8.53, 8.54. So let's call this 8.53 centimeters now to 3 significant figures. So if I use a ruler with 10th degree markings, I can interpolate between those markings to get it to the nearest 0.01 or so centimeters. And then we can have some uncertainty in that digit, but the key is the fact we can interpolate leads us into some of our uncertainties, or leads us into the significant figures that that value contains. So we're certain in these digits with scale 3, and then we're uncertain but still finding significance in that last number. So it's these, or the next example would be imagine you have 2 different items that you measure, or even the same item. If you said you measured it to be 9 centimeters and you're going to add that for some reason to the measurement or some other object which was measured to be 8.53 centimeters, and you're adding these together, well, these are going to add up to 17.53, but we're going to have to round this to 18 centimeters because our plus minus 1 centimeter kind of like rolls out or is like so much bigger than the uncertainty in the 0.01 centimeter value. And so this plus minus here kind of wins out. So we got to go 18 plus or minus 1 centimeter to 2 significant figures. So this will lead into our addition rule, which we'll get into, I believe, on the second slide from now. Okay, so we've used the terms precision and accuracy, or we've at least used the term precision a couple times. So let's talk a little bit more about the difference between the 2 terms, precision and accuracy. So precision, I can think of this 2 different ways. One is the how closely individual measurements agree with each other. So if you put an item on a balance and you keep retaking the mass, usually you're going to get exactly the same mass or very close to the same mass reading every time. We would say that that measurement or that tool is very precise at measuring mass. Now let's imagine a dart thrower. So let's imagine we're throwing darts and we're hitting the same target every time. No matter where the person was aiming, you could say, well, if 3 darts go in the same spot, that's great precision. Accuracy, though, is how close we are to the actual target. So if we were aiming at the bullseye and our 3 darts go astray, then that's pretty bad accuracy, but it's still good precision. So if we hit the target every time, so if we're dead on the bullseye and that's where we were aiming, then we have great accuracy, great precision. And if we're just all over the place all the time, then we have poor accuracy, poor precision. So what does this have to do with anything? Well, precision can also be thought of as that like the 125 versus 125.00, the more digits in a value, the more digits there are, that would be said to make the value more precise. How close that actual value is to the true target is the accuracy of the value. Whenever we use equipment in the lab, we generally assume that it's well calibrated. We might do some tests when we do experiments to try to see how well our results agree with literature findings or some trusted value that helps us test the accuracy of the experiment. And then if we do a couple of trials, helps us test the precision of the experiment. And if you find your experiments are very precise but far off target, then you can at least say, well, there must be something, maybe wrong with the calibration of some piece of equipment that we're using. Maybe we're not using a tool correctly, so we might look at how we're carrying the experiment out. If we're making a mistake somewhere along the way in terms of a repeated mistake or misuse of a piece of equipment, or check the calibration of some devices. And if we're finding our precision is very bad, what we might do is then say, are we following the procedure differently each time? So maybe we're making different mistakes as we go along throughout the procedure. And so it might just help us understand some bit of experimental science and dealing with precision and accuracy. But it's the precision that we're talking about when we follow sig fig rules. So when we start rounding off results or needing to round results, this is following the issues related to precision in the values and the impreciseness of these measured quantities. Okay, so we did the stop problem here today. Imagine you're working in a movie theater and you walk in and your boss says, how many people are in the theater? And you say, I don't know, there's about 300. And so from your eyes, maybe you haven't really counted crowds before. So maybe your plus minus is like literally on the hundreds. So when you say 300, you're maybe thinking the plus minus is on the order of like about 100 people. So there easily could be 200 people in the room. There easily could be 400 people in the room, but probably somewhere around 300 or so, give or take. So a pretty big give or take here. And so then let's say we see 4 people enter the theater or enter the room. So we have 4 people coming in. Can we say there's 304 people? And of course we can. So in this example here, the plus minus 100, sort of outweighs that 4. So we're probably going to have to see a ton of people walk in, about 100 people walk in, before we can really start to adjust that number to be closer to 400. So we sit there for 10 more minutes. We see several groups of people walk in and then take a second look, and now we say, okay, maybe there's 400 people in the room. But we can also we can count people pretty easily if we take the time and the energy it would take to count everybody in the theater, have everybody hold still, give a quick count, double check it, triple check it, and we should be able to come up with a count exactly the same every time. And we come up with a count, let's say we determine in a given theater, in a different example, there's precisely 300 people in the room. So counting objects is exactly precise. If you count 300, you know for sure there's 300. That's not even 3 sig figs. It's like an infinite number of significant figures when you can count or know. Like if you have 2 objects, you know there's 2 objects. I mean, you're precise in that. That's not 2 plus or minus 1. This isn't 300 plus or minus 1. This is 300 plus or minus 0 when you know for sure. So we know for sure, and then we know for sure 4 people walk in. We know for sure then there are 304 people in that movie theater. So we have to be a little careful with sig fig rules because sometimes we deal with numbers that are exact numbers. Sometimes we deal with numbers that are inexact quantities or relating to a measured quantity. And so it's the measured quantities that are going to limit the calculations that we do and the results that we obtain, not these exact or precise values. So let's take a look at a couple different examples here. So let's say we count 12 eggs. You know for sure there's 12 eggs. So that's an infinite number of sig figs. So you're exactly sure that there's 12 eggs. So the meaning is that this isn't 12 eggs plus or minus 1. There's no uncertainty here. There's no uncertainty in that value. We're 100% certain that there's 12 eggs. When we're 100% certain there's not 2 sig figs, there's an infinite number of sig figs, we're not going to look at rounding a number off because of that 12 value. It doesn't happen. This is an exact quantity. 105.0 liters of water. Now we're assuming that this number is given to us because it was based on, or it's mimicking some sort of actual measurement of volume of water that could have been made. And so the implication here is that the uncertainty is plus or minus 0.1 liters. There's some uncertainty in this last digit. So this number here should have 4 significant figures. So number of sig figs are sort of the first digit that's significant to the last and all the digits in between. So I get 4 sig figs here for 105.0 liters. The 0.00305, my first significant digit is the 3, my last one's the 5. So here I end up with 3 significant figures for 0.00305. These zeros that lead the number, those aren't significant. Those are just placeholder values. And so if we express this in scientific notation, we might call this 3.05 times 10 to the minus 2 grams, that this number here clearly has 3 sig figs, and it should match writing it out as the whole number with 3 sig figs as well, and it does. So the leading zeros and the 0.00305 don't count towards the sig fig count. So I need an actual number to kind of kickstart my sig figs. So that number there is representing 3 significant figures. So the key is grams of sucrose is what clues me in that this is some sort of measurement, or implying that this was a measured quantity, or it's portraying a measured quantity of a mass of a compound. Now I have a conversion factor here. 1 inch is equal to 2.54 centimeters. I'm even told that this is exact. There is exactly 2.54 centimeters in an inch. The way this would be interpreted mathematically is there's 2.54 with an infinite number of zeros after it, centimeters in 1 inch. And 1 inch is also has an infinite number of sig figs in it. So you have infinity in terms of the number of sig figs here. We don't want to round results off because of our conversion factors. If you ever find yourself thinking you should round a result because of the sig figs in a conversion factor, we either need to do one of two things. We either need to double check the reality of the sig figs because it may be exact. For example, there's 12 inches in a foot. This isn't 2 sig figs. And if you think that's 2 sig figs, I would argue, then why isn't it 1 sig fig here? This is perfect. This is an infinite number of sig figs. There's exactly 12 inches in a foot. There's exactly 2.54 centimeters in an inch. We'll see in a minute this multiplication rule, but imagine you're doing this conversion here. You're doing 12.25 inches, and you're converting this to centimeters. 1 inch is 2.54 centimeters. That we're going to keep all 4 sig figs. When we see the multiplication rule, we usually start counting sig figs and say 4 sig figs times 3 sig figs. We generally would round that to 3 significant figures, but our conversion factors here have an infinite number of sig figs. So I'm going to keep all 4 significant figures in this result. I didn't actually work this out in class, but why not just take a second here in this video. So 12.25 times 2.54, and then keeping 4 sig figs, this would be 3.112, or 31.12 centimeters. All 4 of those values being significant. So I had 4 sig figs times infinite. I'm going to keep 4 sig figs. I'm not going to round off to 3. And if you ever want to round off to 3, I would say, well, why don't we round to 1? We don't round to 1 or to 3 because that is a perfect conversion factor. So conversion factors are either exact, or they're either much more precisely known than maybe what we're using. Like if you're converting, there's a problem later, but 1 kilogram is equal to, 1 kilogram is equal to 2.2046 pounds. We can even look more digits up than that. But imagine you're doing a conversion where 1 kilogram is 2.2 pounds. If we're doing a conversion here, we're going to want to look up more values. Like that's not precise enough. This isn't the exact value. So this isn't an exact conversion either. This is a value that we can look up to be more precise than what we might need if we're converting, let's say, kilograms to 3 sig figs to pounds. We want to look up our pound conversion to more significant figures in order to not have to round off our result because of our conversion factor. So conversion factors should be and are always going to be much more precisely known than any lab measurement you're ever going to take. And then the last thing is kind of goes back to an interpolation problem, but if we look at our burette here, it's right on the 20, this is milliliters marking, so this is a 20 milliliters for sure. And then it's right on the 0 line, so we know it's 20.0. And then we could have differentiated that from 20.1, from 20.2, from 20.3, etc. So we can even say this is 20.00 milliliters. So you can always take your markings here. If you notice the markings, this would be 20.1, this is 19.9. So the markings are 0.1 milliliters. And so you can always interpolate in between the markings. So you can always get that next digit in between the scale markings. So we could record that to be 20.00 milliliters, or if you had a different case where the meniscus was between, say 19.5, 19.4, the meniscus is like right about here, that's probably 19.45 milliliters. So make sure to interpolate between the scale because there's still some certainty here. Even though we're uncertain, there's still some significance in the value is a better word than certainty. But there's a little bit of uncertainty. Like we can maybe argue if that should be 19.44, 19.46. But the key is it's definitely not 19.40 or 19.50. So we have some significance in that value being about 19.45 milliliters to that number of sig figs. I'll re-record that for whatever. Anyway, so the sig fig rule. So let's look at the first rule for addition and subtraction. So significant figures in calculations when we're dealing with these measured or inexact quantities that are sort of subject to uncertainty in that last digit in the value. So again, remember, it's the least certain measurement or inexact quantity that's going to really be the limiting factor when we start doing calculations relating to significant figures. So let's look at this rule here. So when we add and subtract, results are reported to the same placeholder as the value ending in the greatest value placeholder. And so what we're going to be looking at here are placeholders. So placeholders are like decimal places or the digits that a value is ending in. So 75 ends in what I call the ones placeholder. The other 75 number ends in the ones placeholder. So this result here should be recorded or accurate or given to the number of sig figs to that ones placeholder here. So that means that in 150, all three of those numbers are significant. So I'd record that as 150 to 3 sig figs. One way of thinking of this, or one way of trying to understand why it's 150 to 3 sig figs and not 2, is think of the plus minus. If I have 75 plus or minus 1, plus 75 plus or minus 1, then my plus minus when I add these together is probably from about 148 to 152 is my plus minus. If you take advanced statistics courses or even the intro statistics course, I think you'll go through and learn how to propagate the uncertainties and actually come up with an actual plus minus in the result. And you'll see that that plus minus is falling in that third significant figure. So if we wanted to express this number, we probably want to use scientific notation. If you said, how can I express 150 unambiguously to have 3 sig figs? Because let's talk about a different context real quick. Like let's say in a different context, you're reading a problem and it says you have 150 grams of water. Completely different problem than what we're talking about here. So the problem says you have 150 grams of water. How many sig figs would you interpret that number to be here? The ending in 0 without a decimal point is always a little confusing. The assumption is always going to be that it's just the 2 sig figs that are significant, that this number here must be portraying 150 plus or minus 10 grams with only 2 sig figs. So the implication is that the 5 would be our uncertain digit, and we would have to be told something in the problem to know that that 0 is significant. Now, the usual way is scientific notation. We'll see in a minute when I put the 150 grams below into scientific notation how to use that and how that helps us be unambiguous. Sometimes you might put a decimal point or sometimes an underline under the 0 might help portray that it really has 3 sig figs. But in a problem in this class, we would probably use scientific notation so you would know for sure that that number has 3, not 2 sig figs. And so now if you said, again, in the same context, 1,000 milliliters of a substance, you're interpreting that to be just 1 sig fig, unless you have more information about the 1,000. Now, that helps us understand maybe the sig fig rule for if the value ends in a 0, there's no decimal. Imagine how the problem's different if we said 150.0 grams. Do you see how the decimal point then kind of tells us that the very fact that we wrote that 0 makes it significant? That if we see a problem that says 150.0, that this should pretty clearly be 4 sig figs, without any ambiguity, because we wouldn't have written the point 0 if it wasn't significant to write. So now let's come back to the context of the problem here, 75 plus 75 grams. So if we got to the 150 in a different way, so if you read in a problem 150 grams, we read that to be 2 sig figs, but then you do it on your calculator, you do 75 plus 75, you get 150. We're not saying that's 2 sig figs because your calculator says 150, and we said here that that was 2 sig figs. Different problem, different context. 75 plus 75 resulted in the 148 to 152 result. We're ending in the placeholder that's greater in value. The placeholders for the two numbers are the same. They have the same greatest value placeholder, the ones place. So that gets reported to 150 with 3 sig figs. So we would write this, or could write this as 1.50 times 10 to the 2 grams. And then that's the way to unambiguously write that number, showing that it has 3 significant figures and not 2. So if we carry out subtraction, we again look at the placeholders as well. So this will be 0.01, so this will be 20.01 grams, and all four of those numbers are significant. And so notice when I add and subtract, I'm not counting sig figs, I'm looking at the placeholder. So I'm looking for the greater value placeholder. Now these two subtraction steps end in the same placeholder, so the result is good to that particular placeholder. So let's do the next step here. So the next addition step, again, I can kind of just line up the decimal places and then end up with 129.46 grams. So I can still think of rounding, but I round down because I end in a 4 here. If that ending value was greater than 5 or 5 or greater, I would round up. So we still can round to the uncertain digit here. So I end this number 129.46 grams. So sig fig rules are about finding the greater value placeholder. So the hundredths place is a greater numerical value than the hundredths placeholder. So that's where we round our result to. You can think it's the plus minus in that placeholder that's leading us to round. Now, one last thing, let me erase this a little bit here, is the implication would be that the first mass here, the 125.05, was just measured on a different type of scale or balance than the second mass. So you can use two different balances. We have two different balances in the lab. One goes to 0.2 grams, the other one goes to 0.04 gram, or to the nearest 0.01, the nearest 0.0001 gram. And so if you have two different types of balances, you know, the poorer balance, the one with the less precision, is going to limit the addition step. Okay, so let's look at the multiplication rule. The multiplication rule is actually, I think, the easier of the two rules because it's just looking at sig figs. So in multiplying and dividing, the results are reported to the same number of sig figs as the value with the least sig figs. So of course it's going to be the value with lesser sig figs that limits us here. Now let's think about 75 times 75 for a minute, just to try to see how and why this rule works. When I do 75 times 75, that's 5625 square meters. And so how many sig figs should that be rounded to? Now again, think about, we measured a room to be 75 meters. That's a pretty bad precision. That would be, you know, maybe like using your footsteps, or have you ever walked off like a golf shot or something and kind of walked off and said, okay, this should be about 75 yards. Like the precision there is pretty bad. Like a ruler would get you much better precision than 75 meters. But again, imagine you have such a poor device was used to measure 75 meters. By 75 meters, the area there would actually be rounded to 2 sig figs to 5,600 square meters. Now you can kind of see how the rule works if you imagine the plus minus playing itself out here. Imagine you go 74 times 74 for the low end of our plus minus here for that uncertain digit in the 5's placeholder. That would be 5476 square meters. That's 74 times 74. Whoops, changed color. And then if we do 76 times 76 for like the high end, so just imagine the plus minus, because it's that plus minus that's really causing us to need to do this rounding step. 76 times 76 is 5776. So do you see how that plus minus is falling in that hundreds placeholder value? It's falling in that second significant figure. So that's why we round the number to be 5,600 square meters. Now, we probably don't need to use scientific notation to unambiguously, if you wrote that, everybody would assume that's 2 sig figs. If you want to be certain, you could write 5.6 times 10 to the 3 square meters. But just a way of kind of using scientific notation along with our numbers here. Second example, 4 times 3 sig figs. This is really simple, right? We're just going to round the result to the same number of sig figs as the value with fewer. And so the fewer sig figs is 3, multiplying it by 4. We're going to round this result to have 3 sig figs. So 75 times 5.20. So that's 390. That's what my calculator says. And so all 3 of those digits are significant. And so again, I might use scientific notation. I might use a decimal point or underline it too, but 3.90 times 10 to the 2 square meters. to show that that has 3 significant figures. And then division works the same. So nothing different with division. So these are the multiplication and division rules. So 2 sig figs divided by 3 sig figs is going to be rounded to 2 significant figures. So 7.5 divided by 4.55 goes to 2 sig figs. So that's 1.6 grams per milliliter. And so it's the plus minuses. It's the 7.5 plus or minus 0.1 grams. It's that 0.1 gram uncertainty that's really the limiting factor here. Now, here comes the tricky part. And there's so many different examples of this that, that just deal with multi-step calculations. So what do you do in a multi-step calculation where we're adding here and then we're dividing? Well, we should apply the addition rule when we add. We have to add these 2 numbers before we divide. So we're going to have to do the addition, think about our sig fig rule, and then we're going to have to do the division rule when we divide the numbers. So to track the proper number of sig figs throughout a multi-step problem, we're going to track those rules sequentially through the problem. So I'm going to do 7.5 plus 2.6 first. And so let me do that off on the side here, 7.5 plus 2.6. That's going to be good to the tens placeholder, so that's 10.1 grams. And so now that gives me 3 significant figures before I do that division step in the numerator. So I now have 3 sig figs on the top and then 3 sig figs in the denominator. So I'm going to round this result to still have 3 significant figures. But do you see the tricky part? The tricky part is sometimes the mistake we make in a sig fig problem is we see division, we see 2 sig figs, we think must be rounded to 2 sig figs. But what we had to do though is we just had to add the numbers to get their proper number of sig figs. First is 3. So this problem here is really 10.1 grams to 3 sig figs, all those digits being significant, divide by 4.55 milliliters. So I should have 3 significant figures. So 2.22 grams per milliliter. Now, we could do examples for 20 minutes of this. We could do examples for a day, and it's still going to be a little bit confusing. So I think what we need to do is just practice the addition rule, practice multiplication rule, practice this a couple of times. I think, let me remind myself that the next problem is a similar example. So let me turn this to you guys for a couple of minutes. I'll go ahead and turn the quiz on. Today's quiz password is carbon. And we'll just do this one question for today. So you can do this one question. You can leave the others blank. You can leave blank questions. It's totally fine. You can also, either now or even later, you can still access, you can retake a quiz if you want to take it later and add in anything that you want to add in terms of things that you might be stuck on. But just give this problem a try. Feel free to communicate or compare results with your neighbors. If you're new to the class, this would be in lecture modules. There's a lecture 3 survey. All right, let's take a look at the answers to this one. It's kind of funny. Like the quizzes don't matter if you're right or wrong. If you're concerned, you can always go back after and change your answer. It's not. These are only for engagement purposes, so don't think that if you get a question right or wrong, it's going to impact your grade. But the answer here is D. I actually see a pretty good kind of mix already where some of you have said B, some said C, some said D. Now, the first context I want to talk about is just remembering when we see our calculator says 1200, that's a different context than a problem that might say 1200 meters per second. If you're reading a problem and it says blah, 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 the speed of a particle is 1200 meters per second, you would say, okay, that's 2 sig figs. We would all agree that that's 2 significant figures. But the calculator is saying that's different. The calculator's context is I had 4 sig figs times 4. So my numerator has 4 sig figs still, but then my denominator ends up being 10.00 seconds. And all 4 of those digits are significant because of the addition rule. It's about placeholders. So when I add these numbers, it's not about 3 sig figs plus 3 rounding to 3 sig figs. It's about the placeholders here, and it's about rounding to the hundredths placeholder still with 4 significant figures. So all 4 digits here are still significant. Think about it like this. It's 2.50 plus or minus 0.01 second. 7.50 plus or minus 0.01 seconds. Your uncertainty here is like plus minus 0.01 to 0.02 seconds. We could do the math. I don't want to do the math. Math's terrible. Like that's for statistics people to do. But if you do the math, you'll see that the uncertainty is lying in that zeros placeholder value, that hundredths placeholder. So 4 sig figs divided by 4 sig figs gets rounded to 4 significant figures. So again, to scientific notation, 1.200 times 10 to the 3 meters per second. Now, rarely in this class you do anything on paper that's turned in for a grade. So most of the questions you ever do are multiple choice exam questions or numerical entry-based exam questions. So an exam question like this might say, enter the number of sig figs as a number, so you might be just like typing in 4, hitting enter. You might be typing in, it's actually hard for our exam system to grade sig figs in terms of a number. So there's no easy way for, and you're probably seeing this at that lab, right, which is a nightmare in a lot of different ways. But it's hard for an online system to grade sig figs other than just by asking you how many digits are significant. So rarely do you actually need to convert things into scientific notation, but that's just the proper way to show the significant figures. So we'll layer in some additional examples on sig figs. There's a bunch of examples on the daily quizzes. I think the first 10 daily quizzes have sig fig questions. Once you think you've seen every example, we'll throw a little twist that maybe you didn't see coming, but it's always trying to follow the rules sequentially in the order that you do the math steps. When you add and subtract, follow the addition and subtraction rule. When you multiply and divide, just follow the multiplication and division rule. And that's mostly it, 2 sentences, and then sequentially apply. Okay, so let's get into some talk about units, a little bit into two-dimensional analysis here today. So what prefixes do we need to know in terms of converting like gigahertz to megahertz or things like milliliters to liters? The prefixes we want to know are giga, mega, kilo, centi, milli, micro, nano. And these are in order. So these are in order from the big units to the small units. And so 10 to the 9 is giga, 10 to the 6 is mega, 10 to the 3 is kilo, centis 10 to the minus 2, millis 10 to the minus 3, micros 10 to the minus 6, nanos 10 to the minus 9. And so nano 9, hopefully that helps you remember. But like the way this would be used is thinking of 1 meter, how many nanometers are in a meter? It's a lot of that little unit. So there's going to be 10 to the 9 nanometers in a meter because the nanometer is very small. So a meter has a lot of the nanometers, or 1 nanometer, this is where the minus comes in. 1 nanometer would be 10 to the minus 9 meters. So 1 nanometer is very small, 10 to the minus 9 meters. Micrometer would be 10 to the minus 6 meters. That's the Greek letter mu. So that's the micro. Then on the bigger side, then we'd have that 1 like gigameter, let's say, would be 10 to the 9 meters. So a gigameter is very big, has a lot of the meter. So the biggest takeaway here would be first, just kind of knowing that we're going to use these a fair bit. we use the smaller units probably more than the giga and the mega early in this class, or even more predominantly through the class. So you're going to see the centi, milli, micro, nano way more often than you're going to see the other side of the equation. You're going to see kilograms probably most likely is the other main one you're going to see on the bigger side. But just making sure that we get the minus on the right side. Like when we're thinking the nanometer, very small, gigameter, or the giga prefix, a lot. Okay, so let's do a couple conversions here. So we have 0.000125 seconds. The first part was just making sure we can put that in scientific notation. We've done scientific notation a few times today, but 1, 2, 3, 4. So this would be 1.25 times 10 to the minus 4 seconds. And if we want to do some conversions into megaseconds, that's the capital M is mega, so that's 10 to the 6. And so the way we would do this conversion here is the number of megaseconds would be equal to 1.25 times 10 to the minus 4 seconds. I want to start with what I'm given, that number of seconds. And this is a particularly weird conversion to do because one megasecond has 10 to the 6 seconds in it. So it's not going to make the number like more useful to use in a calculation or to write out. So this is going to be 1.25 times 10 to the minus 10 megaseconds. So not a very useful representation for this number to convert it to megaseconds, but just showing how we can make that conversion. If we want to convert to microseconds, this one might actually help us get the number of seconds expressed closer to a whole number. So the number of microseconds that 1.25 times 10 to the minus 4 seconds corresponds to, this would be the conversion factor that 1 microsecond is very small. That's 10 to the minus 6 seconds. So 1.25. Now, everybody comes from a different point of how often they've done or used these calculations, but 1.25 e minus 4 is how I enter 1.25 times 10 to the minus 4, just giving that kind of reminder. And I'm going to divide this by, and the way I tend to do this is if I'm going to divide by 10 to the minus 6, what I type is I go 1 e minus 6, because this is equal to 1 times 10 to the minus 6, which is equal to 10 to the minus 6. Now, of course, you could have divided this by 10 caret minus 6. There's more than one way to put things into a calculator, but to me, the E button is what has confused probably more students throughout the history of math than anything. Well, I'm sure there's other things in math that are confusing, but 1.25 e minus 4 divided by 1 e minus 6. So that gives me 125 microseconds. Now, one thing to caution, and I see this a bunch, is I see students a lot of times do 10e minus 6. Sometimes, remember e is in a caret button, so don't type 10e minus 6 when you mean to type 1e minus 6, or type in 10 caret minus 6. So if we were going to do 10 to the power of minus 6, that would be 10 caret minus 6. So again, just a few reminders on calculator usage. Nanoseconds, I'm not going to work this out, but this would just be 125,000 nanoseconds. We're going to pick up another 3 digits on the number, or 1.25 times 10 to the 1, 2, 3, 4, 5. Converting that over to nanoseconds. But just a couple examples using those units there. Let's talk briefly about temperature. So we introduced the temperature scales in Chapter 1. Predominantly, of course, we use the degree C scale in this class. We'll use Kelvin a fair bit too. Rarely do we use Fahrenheit, though. If you're a domestic student, that's one we have thought about the most. So we have a couple of equations here that interconvert units. We give you these equations on tests, so if you ever need to do a temperature conversion, you would have access to these equations. Sometimes I just like to show or think about a couple common conversions. Like if we're at 25 degrees C, that's a common temperature in degrees C. What is that in Fahrenheit? 25 degrees C in Fahrenheit, I just plug in the degree C temperature times 9/5. And so that's going to be 9 times 5 plus 32. 45 plus 32 is 77 degrees Fahrenheit. So 25 degrees C is 77 degrees Fahrenheit. A Fahrenheit problem I always thought was kind of funny is the 98.6 degree. This is actually a question from the next slide, but we'll just work on it here. But 98.6 normal body temperature to degree C, we just subtract 32 and then multiply that quantity by 5/9. A lot of you guys probably know the number because you probably know it. Does anybody just know it without even calculating it? 37. So it's 37.0 degrees C. I've often thought that this is like a sig fig mistake, that standard body temperature is probably, like it's not 37.0, it's not 98.6. The plus minus is a good degree on that degree C there. So anyways, but 37.0 precisely would be the proper sig figs for 98.6 converting over to degree C. And then finally, Kelvin is the interesting scale because Kelvin sets the 0 point. It's an absolute scale, meaning the temperature cannot flip into negative in the Kelvin scale. So the lowest possible temperature is 0 Kelvin. We get to 0 Kelvin in degree C at minus 273.15 degrees C. So that's absolute 0. So that's the lowest the temperature can be. That's 0 Kelvin. 25 degrees C will be 298 Kelvin. So 25 degrees C over to Kelvin is 298 Kelvin. That's 25 degrees C. 37.0 degrees C converted to Kelvin, that would be 310 Kelvin to 3 sig figs. Or actually, we can add the 0.15, round that to 310.2 Kelvin. So we can actually get 4 significant figures on that Kelvin. So our temperature scales are shown here. The one thing that's kind of interesting is our Kelvin scale. If you think about the melting versus boiling point of water, 0 to 100 in degrees C, 273 to 373 Kelvin. So in Kelvin, it has the same increment as a degree C scale. So in other words, you go up by a Kelvin, you go up by a degree C. So they're increasing in the same increment. And then the Fahrenheit scale, though, is kind of on its own thing. It's about a 200 degree wide scale for that temperature range, but not precisely 200 degrees. Okay, so we were looking at this conversion. Again, no, if you have to do temperature conversions, we give you the proper equations to make those conversions. We don't expect that you memorize the degree C and degree F conversions. And so then kind of one of the last things I want to wrap up today with is just, and we've used dimensional analysis when we were converting a couple values earlier, but dimensional analysis is a tool we use for converting units. It's also often used in problem solving. So just to give a couple examples here, how many grams are in 2.25 pounds? This conversion would always be given. We don't expect that you memorize just about any conversion factor in this class, or any of the like non-SI to SI unit conversion factors. And so if we want to go to the number of grams, what we have to be able to do is convert 2.25 pounds to kilograms. So it's 2.2046 pounds per kilogram. And then the one we have to know, like the prefix conversions, is the ones we really have to make sure to know, that a kilogram goes to 1,000 grams. And so just for a moment of thinking sig figs, this is mostly multiplication division. So 3 sig figs divide by 5 sig figs. This is actually a rounded value of the conversion. If I needed more, I could look up more, but I don't need to look up any more. And then this is infinite sig figs, right? I'm not rounding to 1 sig fig because of that final conversion. So I'm going to keep 3 sig figs in my result. So I go 2.25 divided by 2.2046 times 1,000. So this would be 1.02. Wait, I wasn't reading the decimal part right. 1,020. So this is 1,020 grams to 3 sig figs. So 1.02 times 10 to the 3 grams to show that clearly to 3 significant figures. Okay, now we can use it for problem solving. We'll talk about cubic conversions. We'll do a few of these conversion problems to start class on Wednesday and then get into some chapter 2 topics. All right, guys, I'll do this for today. Have a great weekend, and long weekend. Monday's a holiday, so I'll see you guys on Wednesday.